Hello everybody. In today's lecture, I will cover matrix exponential. So matrix exponential function, which has the form of e to power at. Okay, and it's very critical for analysis of both continuous and digital control systems. Okay, what's a matrix exponential? We have a time, of course, which is an element of real numbers, and A is a matrix, is a square matrix. It should be square matrix, Rn by n. Okay, so how we can compute or define a matrix exponential? So let's start with the normal exponential function e to power alpha. We can also have t, which is obvious, is equal to, as you remember, it's an infinite series. Starts with 1 alpha t plus 1 over 2 factorial alpha square t square plus 1 over 3 factorial alpha cube t cube, and it goes like this. Okay, so we start the same definition. Okay, so we assume that e to the power at, okay, is an exponential function, but instead of 1, we start with an identity matrix, which is technically a to the power equal to 0, okay, plus a times t plus 1 over 2 factorial a square t square plus 1 over 3 factorial a cube t cube, and it goes like this. So we can write it in a more compact form. E to the power at is equal to, this is technically a definition, k is equal to from 0 to infinity t to the power k divided by k factorial a to the power k. Okay, so this is the metric exponential. As I told you before, it's important for both continuous and digital state space representations. Okay, so one question, I will answer it later, but it's good to talk about now, how we can compute it. Okay, so it's kind of obvious if we have a is a like single state, a single variable, but when it's a matrix, it's kind of can be tricky. Okay, for some systems, indeed, using the definition is very easy, and you can use that. But these are for specific systems, it's not for general case. For some instances, of course, computing the definition is not technically practical, but there are different ways of computing a to the power at, and these techniques are both numerical and sometimes even analytical. Okay, so now let's talk about the properties of matrix exponential. Okay, good. So the very first property is related with the derivative of matrix exponential. Okay, so I start with the claim that, okay, so property 1, it's not claim, derivative d over t, derivative with respect to t, e to the power at is equal to a times e to the power at, okay, and it is also equal to e to the power at times a. Okay, so as you can see, they have two matrix multiplication, that's a and b, let's call it b, okay, and b times a, and they're equal to each other. So it means that these are technically commutative. Okay, so it doesn't have to be commutative for all matrices. Of course, we know that a times b may not be equal to b times a, but in this case, they're equal to each other. Okay, so in my lecture notes, I have the proof of all of the properties. Okay, I recommend you to read and understand all of the proofs. They are kind of nice for intellectual reasons. I will not ask any proof-related questions in the midterms, but I can ask proofs in the projects. Also, I can ask some true-false related questions, which kind of touches or uses some features from these proofs. Okay, so this is the first feature. Okay, so our second feature is, or property, is equal to, okay, let t1 and t2 are two different time instants. They are equal to real numbers. Okay, so we know that a e to the power a t1 times e to the power a t2 is equal to e to the power a t2 times e to the power a t1. Okay, which means they're commutative. It's one property. Moreover, it is also equal to e to the power a t1 plus t2. Okay, so as you may guess, these properties are obviously satisfied with the classical exponential function when we don't have a matrix, when we have a scalar variable. But we show that even in the matrix case, we satisfy some of the proofs which are very handy and useful for analysis for scalar dynamical systems. Okay, this is the second feature. Okay, so what is the third one? Let's look at the third one. proof. Okay, that's nice. Okay, good. So in general, let A be, okay, element of R n by n. So A and B are two different square matrices, and given that A times B is equal to B times A. So if A and B are commutative matrices, then we know that e to power at times e to power bt is equal to e to power bt times e to power at. And proof of this is relatively easy, and it is indeed equal to e to power a plus bt time. Okay, so under the case that your individual matrices are commutative, okay, your exponential functions ultimately are also commutative. Moreover, you can technically combine it in a single exponential function where a plus b in parentheses times t equal to each other. Okay, so you should also note the fact that if, okay, we violate this commutative assumption, okay, if this is the case, then we cannot conclude that e to power at, e to power bt is equal to, it's generally not equal to each other. Okay, bt, e to power at, and moreover, we cannot conclude that these are equal to e to power a plus bt. Okay, so this feature is true under the assumption that a and b are commutative matrices. Okay, good. So we have another important property. Let's look at that. Okay, let's assume that we have a P matrix, okay, which is also n by n. Moreover, it's a non-singular matrix, which means that determinant of P is not equal to each other, or dimension of okay, range space of P is equal to n, or dimension of null space is equal to empty set or 0. Under this case, we have this e to the power P minus a times pt, okay, which is a matrix function where the matrix here is, let's call it a bar, is equal to p to the inverse of P matrix, P to the power minus 1, e to the power at times P. So which means that we can pop out P's from the matrix exponential. And you will see that it's really useful to have this kind of feature for analysis and solving some of the problems related to the state space systems. Okay, so these are the matrix exponentials and its important features, and we will use them to analyze both continuous time systems during the discretization of continuous time systems, to have like a discrete time control path using a digital continuous time system. Okay, so let's remember, okay, how we can solve continuous time state space equation specifically using matrix exponential. Okay, so if you remember, our state space representation has this form, okay, plus bu, okay, we have output equation, which is not very critical, times du, that's great. Okay, so we know that x is an element of R, and okay, so let's assume that it's a seesaw system for now. It doesn't have to be seesaw, but he is element of R. Okay, U is an element of R. Okay, and obviously that's it. Okay, so we have single input, single output state space system, and it doesn't have to be a single input, single output. I made it to clarify things. Okay, so let's concentrate on the case first where input is equal to 0, so it's an autonomous system. Okay, and we have an initial condition x naught. So how we can solve x of t? Okay, good. So if you remember, if you have a let's say x dot is equal to alpha x. Okay, so simple first order differential equation. So what you do is you compute the characteristic equation, but it's a like first order. You start with a guess, right? Okay, what we do is we assume that the form of the solution is in the form of e to power lambda t. We just plug it and compute the lambda, and we find the solution. Okay, so if you do the same thing, so we will start with a guess, and it will be more an educated guess. Okay, so let's assume that x of t is equal to e to the power t at times x0. So you'll check if it's solved a homogeneous equation or not. Okay, so let's plug it here. That's nice. Okay, so d over dt e to power at x naught. Okay, so as you can see, we need to use some of the features now. Okay, that's great. Is equal to, or is it equal to, or minus? Let's compute a times, okay, e to power at times, okay, so x naught. Okay, that's great. So the question is if it's equal to 0 or not. If it's equal to 0, when input like this, so it will solve the difference equation. So let's take the derivative here. Okay, this is t. That's great. So if we compute the derivative, we can easily see that. Okay, let's compute the derivative. Okay, e to the power at, a times e to the power at times x naught. Okay, that's great. Okay, minus a times e to the power at times x naught is equal to 0. It's true, right? Okay, it's 0. So since it's 0, it's technically solves our equation. Okay, we also need to check that if it satisfies the initial condition. Okay, so x0 is equal to e to the power a times 0, which is identity x naught. Also, it's equal to x naught. So we check the initial condition. The form satisfied homogeneous equation. So it is indeed a solution of the equation. Okay, now we will try to, okay, so let's understand if we can use this to find a general solution. Okay, now we will try to find x of t when we have u of t. Okay, is it true? Exactly, we have u of t is not necessarily equal to 0. We can also, let's assume that x naught in this case is simply equal to 0. Okay, so what we will do is, we will do something different. We will start that, okay, let's have a form like this, e to the power minus at times x of t. Okay, so we have a expression. Let's call it f of t or something else. It doesn't matter. Okay, that's good. Okay, that's nice. Okay, we have started with this. Okay, and I want to take the derivative of this. Okay, just try it and you will see that why I'm coming from. If we take the derivative of this, okay, what we should do is, so it's like two parts. We should do differentiation by parts. It is equal to e to the power minus a times t x dot of t. Okay, that's great. Okay, so minus e to the power minus a t. Okay, x of t a times x of t. Okay, as you know from the properties, a can be either here or here. It doesn't matter for our application. That's good. Okay, so let's group it. Okay, this is equal to e to power minus at times x dot of t minus a x of t. Okay, that's great. So we are just going somewhere else. Okay, now we will use it to solve the state space equations. Okay, so what is our state space equation? If you remember, x dot of t is equal to a times x of t plus b times u of t. That's good. Okay, so let's put it here. X dot of t minus a times x of t is equal to b times u of t. Okay, so I already know what it is, right? X dot of t minus a of xt. Okay, so what I can do is I can multiply both parts with this. Okay, very good. So if I do that, e to power minus at times x dot of t minus a times x of t is equal to e to power minus a of t times b times u of t, which is good. Okay, so we are just reaching somewhere now. Now, instead of this, what I can do is use the original expression, which is here. And it states that d over dt times e to power minus at times x of t is equal to, okay, e to the power minus at times b times u of t. Okay, that's great. So we are just now reaching somewhere here. So we have like derivative and an expression in the other side. Let's clean everything and finish everything here. Okay, that's good. So we don't need to now use this. Okay, so we will just go from this point. So what I can do is I can take the integral of both sides, right? Okay, so if I take the integral of both sides, I will obtain that e to power minus a x of t is equal to, okay, some initial condition. Okay, and it is equal to, so we are taking the integral from 0 to t, so 0 to t, integral of this part, which is respect to e to power minus a, okay, tau, because it should be b times u tau d tau. Okay, so it's kind of nice, right? And we have an initial condition, and we have an initial condition of this, so this is at, so when this is t equal to 0, okay, so when t is equal to 0, this becomes x0, so we have x0 here. That's great. Okay, good. That's nice. So what we can do is, since we know that a to the power at minus at, or it doesn't matter, is invertible for all possible of a values, okay, and it will be a mini project problem for you. So we can write that here like this. Okay, x of t is equal to e to power at x0 plus 0 to t e to the power, because I'm just moving a, and let's plug it here, a t minus tau b times u tau d tau. Okay, so this is the general solution of an continuous time state space equation. Okay, as you can see, we didn't neglect that x naught, which is already here, and we know that when input 0, we can already obtain the solution, and when there's input, we have a structure like this. As you can see, this looks like a convolution, and actually it's a matrix convolution. Okay, we have u tau, okay, it's the input, we have it's just constant, and this is, as you can see, this part is looks like t times tau, which likes the impulse response of a system, and it is actually the impulse response of the system. Okay, very good. So this is x of t. Okay, how we can find y of t, which is super easy, because we know that y of t is equal to c times x of t plus d times u of t, and y of t is equal to c times e to power at x naught plus 0 to t c times e to power a t minus tau b times u tau d tau plus d times u of t, and this is not part of the integral. Okay, so I have all of the derivations in a very clean framework in my lecture notes. I really recommend you to look at your lecture notes when also watching these kind of videos. Okay, that's good. So now we will do something else. Okay, what we will do? Okay, we will solve an example. Good. Okay, so, let's clean everything and try to comment on that. Okay, very good. So the most important part, as you can see in this expression, is e to the power at, right? Okay, and I told you that it will be very critical for us analysis of discrete-time constants, and we call it a state transition matrix. It's equal to, it's a function e to the power at. And as you can see, we start an initial condition x naught, and x naught doesn't have to be the like t is equal to 0. We can start our system from any time. We can use the initial condition to predict the future states and future output. Okay, and state transition matrix, which is the matrix exponential a to the power at, determines this mapping from any initial condition, including the input, to any final state. Okay, so let's solve an example and finish this lecture. Okay, that's good. So let's go in that. So, okay, good. So let's assume that we have a seesaw system. Seesaw system, and our input is an impulse function. Okay, our initial condition equal to 0, and the goal is computing y of t is equal to g of t, which is the impulse response of the system. So can we compute the impulse response from the state space structure? Actually, which is very easy. Okay, so we know that y of t is equal to, let's remember, c times e to power a t times x naught. This is already equal to 0 because x naught is equal to 0. We are computing the impulse response. It's equal to 0 to t. We have an integral c times e to power a t minus tau times b u tau d tau plus d times u tau. Okay, so we know that u of tau is the impulse function. So what is the impulse? Impulse is equal to technically a 0 for any value that's different than t, but its integral is equal to 1. So what we do is we simply pop out this part by equating t is equal to 0. So it is equal to c times e to the power a t times b. Okay, it's coming from the input, output, and system matrix plus d times u, not u. Okay, so it's an impulse function. Okay, which is equal to delta t. It's the impulse function. Okay, so if you know c, if you know a and b, you can easily compute that. Of course, the biggest numerical or computation hurdle is computing e to power at, and I will talk about this in the upcoming lectures.